All right, every developer has been there. You're staring at your screen, you need to handle money in your code, and it seems so simple. But pick the wrong tool for the job, and that money, it can literally just vanish into thin air. So how do you make sure your code can actually count correctly? Let's dig in. So this is the question that started it all, coming straight from a developer just like you. You've got money to deal with, and in C#, you've got two main options, double and decimal. I mean, they both handle numbers with decimal points, so what's the big deal, right? Well, as we're about to find out, it is a huge deal. It's the difference between a perfectly balanced ledger and money that just disappears. Okay, first up, let's meet the contenders in this showdown, the double versus the decimal. Think of double as the versatile workhorse. It's the speed demon. It's built to be incredibly fast and handle a mind-boggling range of values, which makes it absolutely perfect for things like physics or 3D graphics. Decimal, on the other hand, well, it's the meticulous accountant. It was designed from the ground up for one thing, handling numbers the way people do, especially money, with absolute, unshakable precision. So I keep using that word precision. What does it actually mean in practice? Let's put these two to the test in a little precision showdown. And here's where the difference really smacks you in the face. A float, which is kind of like double's little brother, gets you about 6 to 9 digits of precision. Okay, double is way better, giving you a solid 15 to 17 digits. But then look at decimal, 28 to 29 digits. It's not even a fair fight. It's in a completely different universe of accuracy. To put that into perspective, look at this number. Just over 1.3 million pounds. It already has 9 significant digits. If you were trying to store this in a float, you'd be right on the edge of a cliff. You're already pushing the absolute limits of its reliability. Go any bigger, and you're basically gambling with the numbers. But what about double, you ask? 15 digits sounds like a lot, right? Well, maybe not. If you're dealing with, say, a large corporate account or a national budget, you can hit that limit faster than you think. A number like this one, almost $10 trillion, well, you've just used up all 15 of your digits. After just a few calculations, tiny rounding errors can start to creep in, and that's not something anyone wants to explain on a balance sheet. So we've clearly established that they are different, very different. But now we get to the really juicy part, why? This is the aha moment that changes how you look at these types forever. Deep down in their silicon hearts, computers think in binary. You know, ones and zeros. It's called base 2. And types like double and float are built to speak this native language. It's super efficient for the processor, but it creates a very, very strange problem. And here it is. This is the smoking gun. In the binary world that double lives in, 0.1 plus 0.2 does not equal 0.3. I know, it feels like it should break the laws of physics, but it's true. The computer gets an answer that's incredibly close, but it's not exactly right. Why? Because a simple number like 0.1 can't be perfectly represented in base 2. It becomes an infinitely repeating number, and the computer has to chop it off somewhere, creating a tiny error. Here is the perfect analogy. It's the exact same problem we have when we try to write 1/3 as a decimal. We write 0.333, and that 3 just goes on forever. We have to stop writing eventually. For a computer, using binary math, the number 0.1 is its 1/3. It's an infinite problem, and that little piece it has to chop off is where all the trouble begins. So how does the decimal type solve this mess? Well, it's simple. It kind of cheats. It just refuses to play the binary game. Instead of base 2, it uses base 10, the same system we humans use every day. So when you give it the number 0.1, it stores exactly 0.1. No weird conversions, no infinite fractions, no rounding errors. Problem solved. Okay, now that we know the why behind all this, let's look at the real-world impact. What really happens when you choose the wrong tool for the job? Imagine this scenario. You're storing a massive number, say 100 quintillion, using a double. Then you perform a simple operation. You add one single dollar. So what's the result? It's still 100 quintillion. Wait, what happened to that extra dollar? It just vanished. Poof. It was so tiny compared to the main number that it got lost in the rounding. It fell below the double's precision threshold and was literally erased from existence. But listen, this doesn't make double a bad guy. It just means it has a different job. Think about this great example. If you're in a video game and you launch a barrel of explosives a quarter mile away, are you going to care if it lands a 1/16 of an inch off target? No way. You care about the speed of the game, the performance. And for that job, the speed of a double is exactly what you want. So after all of that, it's time for the final verdict. What is the one unbreakable rule we should take away from this? And the rule is refreshingly simple. If your numbers absolutely must add up correctly, if they have to balance perfectly with 0 errors, there is only one choice. End of story. So what are we talking about here? We're talking about money, of course. We're talking about financial calculations, even things like high scores in a game. Basically, any number that a human would calculate by hand and expect to be absolutely, positively, 100% exact. So when it comes to money, let this be your mantra. Say it with me. Decimal, decimal, decimal. Except no substitutes. That is the key takeaway. It is the very reason this data type was invented. And that leaves us with a final, lingering thought. For money, the choice seems clear now. But this whole discussion really gets at the core trade-offs in programming. What happens when that line gets blurry? What if you're in a situation where you're forced to choose between that absolute precision and maximum speed? And could you sidestep the whole issue just by using integers to represent sense? It's a great reminder that in programming, understanding why you choose a tool is every bit as important as knowing which one to pick. Thanks for digging into this with me.